Welcome to this talk on dequantizing the quantum singular value transform with applications to quantum chemistry and the quantum PCB conjecture. This is joint work with François and Gall. My name is Sevag Gharibian. Most people just call me Sev. So what is the theme of this work? The theme of this work is this really natural question, right? Which is, where is the boundary between the power of classical versus quantum computing? And of course, this is a really broad question. So for this talk, we're really going to sharpen this into kind of three guiding questions. These are as follows. The first is, if we want to talk about a boundary between classical and quantum computing, we want to rigorously define this boundary. And so in the last few years, there have been a number of really nice works along two different directions that do exactly this type of thing. Number one are these so-called quantum advantage frameworks, like things like boson sampling, random circuit sampling, and so forth. These are trying to make classical computers look bad, for example. And on the flip side, there have been these really nice dequantization works via sampling assumptions, and these try to make classical computers look good. The second thing we care about is, if we're trying to find a boundary between the power of classical and quantum computing, ideally we want this to be a boundary based on some meaningful practical task. So in the long term, of course, that practical task would be something like Shor's algorithm, right? Because nobody believes, at least for the most part, right, that factoring can be solved efficiently classically, right? But in the lab, the field is nowhere near, unfortunately, being able to actually run Shor's algorithm at a large scale, right? It's really difficult to build these computers. So in this work, we'll touch on something that maybe in the shorter term might be a meaningful alternative. And last but not least, whenever we have such a boundary between the power of classical and quantum computers, this typically implies something about the differences between the underlying models of physics, right? So for example, the quantum PCB conjecture, which has infamously resisted efforts for many years now. If it's true, what it means is that natural quantum systems can be really, really complex, even at high temperatures. Good. Okay, so these are the guiding questions for this talk. And the goal of this work is to take those questions and to weave them into one narrative. And the way we do that, I'm going to outline on this talk in terms of 4 bullet points at a high level. The first thing is, of course, if we want to define a boundary between classical and quantum computing, we want to use a practically motivated problem. And that's going to be the so-called problem GLH, which I'll define shortly. This we took right out of quantum chemistry. And I want to be clear that in order to solve this problem to the precision that chemists care about, you want to solve this to within inverse polynomial precision in the size of your system. Having defined GLH, the next thing we'll do is we'll show that this problem is actually easy to solve classically if, number one, you only care about constant precision, and number two, you assume these standard sampling assumptions are available in your computational model. And the way we do this is essentially we dequantize the so-called quantum singular value transform in the setting of sparse matrices and constant precision. So now when we return back to the setting that quantum chemists care about, this 1 over poly precision setting, we next show that this problem is actually going to be BKB hard in the worst case, meaning that if you can simulate this problem efficiently classically, then you could also efficiently simulate any efficient quantum computation classically. So BKB is the quantum analog of P. And finally, I'll try to tell you a bit about what all of this has to do with the quantum PCB conjecture. Good. So let's start with the definition of the problem GLH. So GLH is basically going to have to do with quantum constraint satisfaction. So let's go back to the very beginning and talk about classical constraint satisfaction first. Okay, so I assume many of you, of course, are familiar with this. So the starting point is max KCSP. This is just going to be a problem on n bits, right? And you've got you've got Boolean constraints, each of which act on k constraints at a time, variables at a time. So k might be 2 in this example. And of course, we want to know what is the maximum number of constraints we can simultaneously satisfy over all assignments to these n bits. This is the canonical NP-complete problem that we know and love. So naively, you might ask, what happens if we talk about a quantum analog of this where you have quantum constraints on quantum bits? And that's actually not too unnatural to define. It's actually quite natural. So for this talk, I'm going to just define quantum systems in this way. Okay. So classically, if I have a 2-bit system, right, that takes one of 4 values, right? 0, 0, 0, 1, 1, 0, 1, 1. And the only difference in the quantum setting, at least for this talk, is that instead of being in one of those 4 states, a quantum 2-qubit system can be in all 4 or multiple of those states at the same time. And the way we formally model that is we represent each of those 4 states as basis vectors for C4, so they're just vectors now. And now we take a superposition, meaning we just add these vectors in this vector space. And so what you need to know for this talk is that if I have an n qubit system, the corresponding quantum state is just going to be some unit vector of dimension 2 to the power n. Okay, so the dimension of the space grows exponentially with the number of qubits. So quantum states are just unit vectors in this giant space. And so if my states are just going to be vectors, right, the obvious way to define a quantum constraint is, you want to force this vector to lie in some subspace. So quantum constraints are going to ask things like, okay, I'm going to force qubits 1 and 2 to lie in a certain subspace. Okay, so maybe you want it to lie in the span of these two basis states. Okay, so here's kind of the subspace we want to lie in, and here are the evil stormtroopers forcing us to lie in the subspace. Good, so these are quantum vectors, or states, and constraints, and based on that we can formally define the notion of a quantum constraint system, or a k-local Hamiltonian as it's called. And what is this? This is just going to be sum of local quantum constraints, hi. These are the local constraints, hi. Each of these are just constant size matrices because they act on just a constant number of qubits k at a time. And when we add them up, we'll get a global operator h. This is some giant 2 to the n by 2 to the n matrix. It's symmetric, it's got real eigenvalues. And this is our quantum CSP as a whole. Okay, but of course it has a succinct representation in terms of these constant size matrices. And what are we trying to do? Ultimately, the only thing we care about for this talk is the smallest eigenvalue of h. Okay, and of course, normally that's an easy thing to figure out, but the point is that h is exponentially large here. And so why do we care about the smallest eigenvalue? Well, it turns out that h represents the evolution of the time evolution of some quantum system in nature, and the smallest eigenvalue of this operator tells us, if I were to take that quantum system and cool it to essentially absolute zero, what energy level does my system settle into? That's the ground state energy. Okay, so and at that energy, of course, there's going to be some corresponding quantum state that the system settles into. That's just going to be the corresponding eigenvector to this eigenvalue. Okay, and that's what we call the ground state. Good, so that's a quantum CSP, and now with that in hand, I can tell you about this canonical quantum K-sat problem, let's say, or K-local Hamiltonian problem. And the problem is defined as follows. I give you one of these quantum CSPs as input, h, and I give you two promised thresholds that are at least 1 over Pauli separated. That's very important. And your job is to tell me, is the ground state energy of h, the smallest eigenvalue, small? Is it at most alpha? Or is it large? Is it at least beta? So we've known that this problem is essentially the canonical QMA complete problem for 20 years now, QMA being the quantum analog of NP. What I also want to mention here is that, because we'll touch on this later, is that if you play with this threshold here, this gap, and you ask what happens if I only want constant precision in solving for this ground state energy, well, that's precisely the regime of this quantum PCP conjecture. Okay, and it's conjectured that this problem remains hard. What we certainly do know is that you can embed classical CSPs into this framework, and then because of the classical PCP theorem, we know that in this regime it's at least NP hard, okay, to solve this local Hamiltonian problem. Good, so that's the K-local Hamiltonian problem. This is what we as theoretical computer scientists, love to play with and pretend that we're important, right? But in the real world, actual quantum chemists who actually want to solve this local Hamiltonian problem in practice, we need to ask, what are they doing, right? And here I really want to point your attention to this really nice Simon's Quantum Colloquium talk by Garnet Chen. If you're interested to learn more from a quantum chemist perspective about what's going on, go see this talk. It's a really good talk. But what do they do? In practice, what they first do is they use a classical heuristic, okay, to try and find a good so-called guiding state, psi. Think of psi as an approximation to this optimal quantum assignment, this ground state. Let me be clear. These are heuristics. They run in Pauli time, but there's absolutely no guarantee they're going to find a good guiding state, or we don't even know, of course, that in general a good guiding state even exists. Okay, so in particular, we don't believe that in general it exists. Let me be clear. But at least for some settings, in practice, these heuristics can work very, very well. So the idea is supposed to be, you first compute a good guiding state, and then once you have that, you've got a quantum computer at your disposal. Then what you do is, you're trying to just figure out an eigenvalue of this operator, given an approximation to the corresponding eigenvector. Somebody with background in quantum algorithms would immediately spot now that, okay, we just need to run phase estimation. Okay, and you don't need to know what phase estimation is, just know that it does the job you need it to do at this point. Okay, there are more recent approaches which are heuristic based on variational approaches, which I will not touch on in this talk. Good, so if this is what quantum chemists are doing, then this is exactly what we need to formalize. Okay, so this is the guided local Hamiltonian problem. It is exactly the local Hamiltonian problem, except for these two lines you see in red. So what we've added here is that in addition to the quantum CSP, you've got as input some representation of your guiding state psi, and you're promised that this psi has a good overlap with the ground space. Okay, you don't need to verify this promise, of course, it's just a promise. And let me also be clear that, I could care less how you got your hands on this guiding state psi. Okay, just imagine somebody gives it to you, and now the question is, how hard is this local Hamiltonian problem? That's all this formalization is asking. Okay, now we need to be very clear as TCS people, right? What exactly do we mean by a representation of psi? Because we cannot hope to write general psi down with a Pauli number of classical bits. So in this work, we'll use two representations. The first is so-called sampling access. And here we'll show that GLH is classically solvable if you only demand constant precision, giving access to a guiding state of this form. And on the flip side, if we return back to GLH to within that 1 over Pauli precision that chemists care about, we show that if the representation is a so-called semi-classical state, then this problem becomes BKB hard. Okay, so this is everything I'll say about defining GLH. Let me just take a brief moment to tell you about the punchline at this point. So what we'll show is that GLH is basically BQP hard to within 1 over Pauli precision. On the flip side, it's also in BQP because it can be efficiently solved on a quantum computer to within that 1 over Pauli precision. And so we conclude that GLH to within this 1 over Pauli precision relevant for quantum chemistry precisely characterizes the power of efficient quantum computation. So the obvious thing to ask is this GLH, is it a practically meaningful task perhaps to try and demonstrate experimentally quantum advantage in the near term? And that's exactly, of course, what quantum chemists are working on. This is that talk by Garnet Chan that I mentioned. And so here, let me be very clear, right? Our result is a worst case result. And in contrast to these other really nice results like random circuit sampling, boson sampling, there you're really trying to get average case hardness results in a noisy model. The bar for hardness is much higher there. Okay, so we're doing worst case results in a noise-free model. So you should really view our work as the first baby steps towards something like an average case noisy hardness result. Good. Okay, so that's the punchline for GLH. Now let's move to showing BKB hardness within 1 over Pauli precision. So to do this, remember I need to sharpen now for each of the results, what is our notion of a guiding state? What's the representation? And I'm going to define this notion of a semi-classical state on this slide. So what is a semi-classical state? If you're familiar with this work of Grillo, Karanidis, and Skora, it's basically what they call a subset state, meaning you just take a subset of n-bit strings, S, and you just put your state into an equal superposition over those strings. Okay? So it's a very simple class of states. What's an additional restriction in our setting, which is important, is that we restrict the subset S to be polynomial in size. So the number of strings in the superposition is polynomial, and so psi has a very clean classical description. And what we show is that in the setting of 1 over Pauli accuracy, if you're given one of these semi-classical guiding states, even with constant precision with the ground state, so it has very high overlap, this problem remains BKB hard. Okay, so we don't believe a classical computer should be able to do this. Good. So how do we do this? I won't have time to go into the details, but I'll give you the very high-level tools. The idea is as follows. We're trying to embed an arbitrary BQP circuit, U, which is some sequence of 2-qubit gates, into an instance of GLH with a Hamiltonian H in a guiding state psi. And what we need, of course, is two things. Number one, if the circuit U accepts its input, then we want this Hamiltonian to have a small ground state energy. Otherwise, if U rejects its input, then we want H to have a large ground state energy. And in addition, we need in both cases the guiding state to have a good overlap with the ground space of H. Now, so these are the two conditions we want. The left side we more or less get trivially. It's not trivial to show, but the work has been done, okay? In the sense that you can just plug in essentially this Feynman-Kitaev circuit to Hamiltonian construction of Kitaev. This is basically the celebrated quantum Koch-Levin theorem. And that'll literally essentially give you just this, okay? Now, of course, in our setting, what's different is that we also need to design this funny guiding state, right? And for that, we'll need to modify H further. And to do that, just at a very high level, we use an additional tool. We're going to steal this very nice, elegant idea of understand binus. And here he had this block encoding idea that came from a totally different context, the study of p to the QMA log. And the reason why we use this basically is because it gives us full control over what the ground space of H will look like in the null case. Okay, and if I have full control over what that ground space looks like, then I'm quite flexible in how I can define this ground state psi. That's the idea. Okay, but I don't have time to say more. So this is basically all I'll say about our BKB hardness result. Good. So now let's move to the positive result, the classical tractability. And this was within constant precision. And so here, the representation of the state psi we'll use is what I'll call a sampleable state. And I'll define that in just a second. The algorithm doesn't just work for local Hamiltonians, it also works for sparse Hamiltonians. Okay? Good. So what exactly do we mean by sampleable state? So sampleable state is a messy definition, but first we can ignore zeta really. Think of zeta as just an error parameter, and basically our results will hold even if there's some error in the sampling zeta. Basically that's what the reason why I've left it here. But for this talk, of course, you can just imagine that zeta is 0. Okay, so we're going to have perfect sampling access to some vector psi. What does that mean? That means two things for this talk. Number one, query access. So this is kind of like a bread and butter type of access we love to use in quantum computation, which is that I pick an index I from 1 to 2 to the n into this vector psi and I assume that there's some classical polynomial time algorithm that will compute the ith amplitude of this vector, entry of this vector psi I. So that's query access. The problem, of course, is I'm a classical computer. Query access doesn't do me much good. This vector is way too big, right? I cannot query this thing in superposition. So sampling access tries to alleviate this, right? It says, okay, look, I'm also going to allow you to sample from some distribution p over the indices. And the idea is that the odds of getting any particular index will scale with the weight of the corresponding entry in the vector. Meaning, if I have elements in my vector which have very large weight, well, then I'll be very likely to see those indices, right? It's helping me zoom in on those heavy entries of this vector psi. Okay? So that's what we're going to mean henceforth by sampling access. And when zeta is 0, this is essentially just Tang's original definition from her celebrated breakthrough work on dequantization of recommender systems. Good. So that's the definition of a sampleable state. What do we show? We show basically that in the constant precision setting, if you give me one of these sampleable guiding states, then we can solve this GLH problem efficiently. Okay? So within constant precision. How do we do this? So here's the outline for the proof, basically, or the proof components on this slide. Of course, I don't have time to go through all of this, but the basic premise is as follows. We first take GLH, which is an eigenvalue problem, and we reduce it to a singular value problem. And I hope you believe me that this is possible, because estimating singular values is more general than estimating eigenvalues. Of course, this is also in the guided setting to within constant precision. Once we're talking about singular values, that's where the connection to the quantum singular value transform shows up. So that's where we dequantize this. And to plug this result back into here, we need to specify some polynomial p. We'll see this shortly in the definition of the singular value transform. There'll be some polynomial. And basically what we do here is we apply some polynomial to our matrix, and that, very roughly speaking, allows us to process the eigenvalues of whatever matrix we're interested in, or the singular values, and it will stretch them apart. It'll pull them apart so that I can very easily, or more easily, distinguish where exactly my singular values lie in my matrix. Okay? And what's really important for this talk is that why do we need the constant precision setting? Well, that's crucial because that allows us to choose this polynomial to be constant degree. And as you'll see on an upcoming slide, the runtime of the entire thing will depend exponentially with the degree of this polynomial. So constant degree is very important. Good. So let me tell you about this last step here. On the slide, let me first define what we mean by the singular value transform. So, this is a nasty definition. All you need to know is just stare at this thing here. And so what is this saying? It says the following. First, as input, you have two vectors, u and v. For simplicity, just assume you have sampling access to both. Technically, you only need it for v. And you're also given query access to some giant matrix A, to which we assume is sparse. Okay, it's S sparse. And you're also given some polynomial p. Okay, so what is this thing very roughly doing? It's basically taking a singular value transform of A, like the singular value decomposition from linear algebra, and then processing the singular values by this polynomial p, roughly speaking. And so then you take this operator and you sandwich it. You take the expectation against u and v dagger, basically. Okay, so it kicks out a scalar. Good. And your goal in this problem is to estimate this inner product to within some added error epsilon. What's the connection to the quantum SVT? Well, the quantum algorithm literally outputs this vector here, u times p, basically. Okay? But in principle, of course, for this talk, this is just some linear algebraic definition. There's really nothing quantum about it. And what we show is that you can estimate this quantity, okay, to within epsilon precision within this time. And again, I really want to stress here that the degree of the polynomial d, this is this polynomial, that needs to be constant in order for this to be polytime. Okay, and that we get precisely because the precision is constant time. This d will end up depending on the epsilon as well, which is constant in our setting. Good. So how do we prove this lemma? Here's the idea. Okay, it's going to be similar to what Tang does in our 2019 work, and the way we do it is, I want to compute this inner product, right? Here it is, right? And what's an inner product? An inner product is nothing more than a sum of many terms, right? Where you pick an index on the left-hand side, so I'll pick the jth index of v, pick the jth index of this vector on the right-hand side, multiply and add them to your running total. That's an inner product by definition. And of course, the problem is that I don't have time in this setting to go through all exponentially many entries in this inner product. But what I do have is randomness, right? And in particular, I have this really nice kind of randomness where I have sampling access. It'll allow me to zoom in on the heaviest entries in V, quickly in some sense. So the natural thing to try, of course, is, well, why don't we just pick random entries of V according to that sampling access, and then just compute the jth, get a jth entry here, get a jth entry here, multiply them together, and then kind of rescale, because of course we're adding too few terms, so we need to rescale, and then take some sort of mean. Okay? And that's precisely what we do. So in a bit more detail, we repeat the following r times, where r depends only on the position. And on the left-hand side, we use this very nice sampling access we have to v to pick an index j corresponding to the weight of the entries. So larger weight entries will be seen with higher probability. That'll give me some index j on the left-hand side. And of course, I want the corresponding entry at j. And so for that, I use the query access part of the definition of sampling access. That gives me vj. And now the right-hand side, I need to compute the corresponding jth entry there. And it turns out this we can also do classically, efficiently. We need a recursive technique here, but I won't have time to go through it. But the key point I want to tell you about is that this is only possible classically efficiently because we're assuming S is polysparse, essentially. S is a polynomial, so A is polysparse. Okay? So this gives me the vjth entry on the left, the wjth entry on the right. So basically now I just kind of multiply them together and rescale appropriately and add them to my running total. At the end, we apply Chebyshev's inequality, and we'll get a high probability bound that we're within the desired epsilon estimate with high probability. Okay, so this is how we do that last part of the proof in terms of dequantizing the so-called quantum singular value transform. Good. Now we come to the last point, which is what does all of this say about the quantum PCP? And to tell you about that, let me just briefly remind you, in the scale-local Hamiltonian problem, we wanted the precision to be 1 over poly, and the PCP conjecture claims that even in the setting of constant precision, this problem should be QMA hard, quantum NP hard. And now, using the techniques we've just used, what we can show is that precisely in this regime, in this constant error regime over here, the local Hamiltonian problem, if we assume that there's a good sampleable guiding state, okay, then there's no way quantum PCP can hold, because we can show that this problem will fall into MA, okay, Merlin-Arthur, which is the randomized analog of NP. Of course, in practice, I don't think anybody really exists such a good guiding state to exist in general. Okay, so the obvious thing to do here is that we can't prove the non-existence of the state, so we just conjecture it, right? And to do this, we're going to blatantly copy this very nice NLTS conjecture of Friedman and Hastings. Let me tell you in a moment what this is about. What this says is that, look, if you believe the quantum PCP conjecture, then what should certainly be true is that there should be some family of Hamiltonians out there whose low energy states just do not have a nice classical description. And in particular, the choice of states they choose in this conjecture, the bar is very low. They're just talking about constant depth quantum circuits. Okay, states you can prepare with these. These things can actually be verified in NP if you only care about verifying a local observable, a local Hamiltonian. And the claim is that, this conjecture states that such a Hamiltonian should exist, so that all of these low energy states, if you try and just use a constant depth quantum circuit, you cannot get a low energy state. You're very far from this by some additive constant. And we're going to blatantly just copy this. We'll call it the NLSS conjecture. And instead of having a constant depth quantum circuit for this low energy space, we'll talk about a perfect sampling access circuit or a state. And the claim is that, of course, there should be some family of local Hamiltonians where any sampling access state should not be able to access that low energy space. You should be epsilon away from it. Okay, that's it. So thank you very much for your attention on behalf of both François and myself. If you have any further questions, of course, you're welcome to email us directly. Great. Have a nice